Hello, this is Huffman, Trees, and Entropy. First, I don't know if you can read that. I am assuming you already watched Tom Scott's video on Huffman trees. And so this is going to be the first in a long series of videos on information theory. And the sort of most fundamental quantity in information theory is this thing called entropy. And it's very much related to Huffman trees. And I'm not going to really go into that in a lot of depth here. That takes a lot of work. I am going to sort of give you maybe a bit of a teaser for the whole playlist. Okay, so let's talk about entropy. So the entropy of a probability distribution on, we're strictly for now talking about finite distributions. So there's a finite number of things that could possibly happen. So for instance, you're reading a file and there's a finite number of characters that could possibly come next because it's ASCII or something like that. And it's this really long formula. What I want to tell you what it is, though, the entropy is a measure of the amount of randomness in a probability distribution. So how random is a probability distribution? And it's this formula. So it's minus the sum over, so h of p is equal to minus the sum over every event x of the probability of x times the base 2 logarithm of the probability. And I don't know if I mentioned there's a minus sign here. That's really important. The unit of entropy is bits. Entropy, I said that, it means the amount of randomness in the distribution. Sometimes entropy is called uncertainty or information. I don't like the word information here because it's sort of ambiguous. I will use the term potential information sometimes to emphasize that it's information you don't have, so it's uncertainty. So facts. Here's the formula again. I use the notation. Oh, I turned it on eraser mode. That's why. I use the notation. Let me make that much smaller. I use the notation LB to mean binary logarithm. So that's what that means. So let me list these facts right away, and without getting into too much gory detail. First, entropy is, let's go way to the bottom. There's 3 facts here. Number 1, if there's only one outcome that's possible, so you have some list of possible things that could happen, one of them has a probability of 1 and every other one has a probability of 0. The entropy or the uncertainty of that distribution is 0 bits. Okay, so if you know what's going to happen, there's no uncertainty. Great. Number 2, if you don't know what's going to happen, so it's not just a guaranteed distribution, then the uncertainty is positive. And the uncertainty is maximized on a uniform distribution, so where every outcome is equiprobable. Okay, that's what these 3 facts are, but let's go into establishing each of them. And it's really trivial, it's just some algebra. So, first here, there is a little bit of subtlety, so here's the formula again. If p has one outcome foo, where probability of foo is equal to 1 and probability of everything else is equal to 0, then entropy of foo, or entropy of p is equal to 0. You do have to do this annoying thing, because if you just try to directly plug, so the proof is that you plug in, you say, you plug in 0 for every value of x except 1, so p of x equals 0 for every event except foo, and p of foo is equal to 1, so you get a bunch of terms that are 0 times the log of 0 plus 1 times the log of 1. Okay. 0 times the log of 0, that's not strictly technically defined because it's 0 times minus infinity. However, for the purposes of information theory, you define 0 times log of 0 to be equal to 0, and the reason is just a continuity argument, which is that if you plot minus p times log p as p approaches 0 from the right, the limit of minus p log p is equal to 0. Okay, so we say 0 times the log of 0 is equal to 0. So you get a bunch of sum terms here of 0 times log of 0, which is 0, plus 1, which is 1 times log of 1, which, again, log of 1 is equal to 0. So every term, if you have this configuration of the probability distribution, then every term in this sum is equal to 0, therefore the whole sum is equal to 0. Good. In other words, a guaranteed event contains no uncertainty. That's a great property to have of uncertainty. Okay. Likewise, if P is not a guaranteed distribution, so there's some uncertainty, then there is some uncertainty, meaning that the uncertainty is positive. So uncertainty in particular is never negative. That's what I really want to establish here, and that it's either 0 if you know what's going to happen, or it's positive. Okay. And it's maximized when the distribution is uniform, because obviously that a distribution where every event is equally likely, that's obviously the probability distribution with the most uncertainty. So this is at least a sane formula. Okay. If P is not a guaranteed distribution, then the entropy of P is greater than 0. Okay, let's establish this. So, the way you establish this is by establishing that in this sum, there's no term in this sum that's negative, despite this minus sign. The reason is because logarithm of probability is always between 0 and 1, so the logarithm of probability will always be negative. However, that's why you put this minus sign here. So every term in this sum is either going to be 0, if it's 0 times log of 0, or it's going to be a positive number, which is positive probability times minus logarithm of positive probability. So in particular, you move the minus sign inside here. Well, logarithm of positive probability, that's going to be logarithm of a number between 0 and 1, which will be negative. Minus sign means that it's going to be positive. Okay. So, you have a sum here of a bunch of numbers that are either positive or 0. At least one of them is going to be positive because we've eliminated the case where it's a guaranteed distribution. So at least one of them is going to be positive times positive. None of them are going to be negative, so therefore, if P is not a guaranteed distribution, so it's not all 0 log 0 or 1 log 1, then entropy is going to be positive. In other words, all non-guaranteed distributions contain positive uncertainty. Number 3, entropy is maximized on a uniform distribution. I am not going to prove that, and the reason is that I couldn't find a proof that I liked. I am going to prove it eventually in a different video. Probably, I haven't really decided on which proof. I'll probably use multiple proofs. But that's not really what I want to talk about in this video. I don't want to get into gory details of proofs unless it's really obvious. Intuitively, obviously, a measure of uncertainty should be maximized on a distribution where every outcome is equally likely. Obviously, that's the distribution with the most uncertainty. So that fact, which is true about this, which I'm not going to prove right now, that shows that at least this is a sane candidate. Okay, so, and it's equal to the binary logarithm of the number of possible outcomes, and you get that by just plugging, you say there's n possible outcomes, you plug 1 over n in for p of x, and then you do some algebra, and this comes out to be equal to log of n. Okay, and this is a sharp inequality, meaning that if you have any distribution which is not a uniform distribution, it has an entropy that is less than log of n. That's important. So, in particular, if you have some distribution and you can prove that its entropy is equal to log of n, where n is the number of outcomes, then you can conclude that it's a uniform distribution. So, entropy is equal to 0 if and only if it is the guaranteed distribution. So, entropy is equal to log of n if and only if it is the uniform distribution. Otherwise, entropy is strictly between 0 and log of n. Okay. Let me show you, oops, I typed :W. So, again, I'm assuming you watched Tom Scott's video. Here's another E script, and so all this does is implement the algorithm in Tom Scott's video. So we have some types here for a binary tree. I'll, of course, include a link to this. Let me blow this up and make sure you can really read it. I will, of course, include a link to this, but it's not a very interesting program. What is interesting is the end of the program. So, it's not a very difficult algorithm to write. You can read this if you want. It's not a very interesting program. That's not what I want to show you. So let me just walk through how it works. So it reads the file. If you don't give it a file name, it loads up www.txt, which is the file name for the Wild Wild West lyrics, which I copied off of Google. Main, so it reads the file, converts it to a string, takes the char mults, which is it just counts every character and the number of times it occurs. Then it sorts it. Then we take the character leafs. So it converts, this is converting it into the type for the binary tree. So obviously every character is going to correspond to a leaf. Then it runs the Huffman algorithm to convert that list of leaves, which is sorted, into a tree. Pretty print the tree. Calculate the total number of symbols by just, I'll explain what that does in a minute. Calculate the total number of symbols. Then calculate the entropy of the distribution of the probability distribution on characters. Then it computes the average code length of the tree. So remember, every leaf on the tree will correspond to some sequence of finite sequence of ones and zeros. Okay, and all it does is, according to the probability distribution on the characters, calculates the average code length. So what is the average? Meaning, if you just got some sequence of characters as your sample size goes to infinity, and you got your characters just randomly, independently, according to this probability distribution, a sequence of independent and identically distributed events, what would be the average code length? Obviously, language is a little bit more structured. The characters are not independent and identically distributed, but we're going to ignore that for now. Entropy, average code length, then it prints the entropy of the distribution of characters, average code length through two methods because I didn't trust the recursive method. And again, you can read the code to find out how that works. And then we get out of here. Okay. And okay, let's run it. So here it pretty prints the tree. I didn't put a lot of work into that because it's not very interesting. So a stem. The one thing I do want to note, which will be important later, is that these values, these multiplicities on adjacent branches of the tree, are always very, very close to each other. So 161, 164, 184, 187, 674, 762, etc. Okay. Keep going, keep going. Here's the whole binary tree. It's not very interesting. I mean, it kind of is, but not really. Alright. Here's what is interesting, and this is what's interesting. The entropy of the distribution of characters is 4.47 bits. The average code length is 4.51 bits. That's really, really close. And it's equal regardless of which method I chose. That's all I'm going to say for now, that these two are really close, and they are in fact related. But I think that's all for this video. Thank you.